Hey everyone, my name is Kevin Bach. I'm a PhD student at the University of Maryland, and joining me here for this talk is my advisor, Dave Levin. Our primary work has been studying how censorship around the world operates and how we can use that knowledge to evade censorship and empower those living within censoring regimes. Our recent works, though, have shown that censors pose a much greater threat to the broader internet than previously understood, and that threat is what we're here to talk to you about today. Now, before I get into that, I wanted to first offer a quick high-level recap of how nation-state censors operate at the network layer. So, let's say we have a client, such as a web browser, and this person can be located inside a censoring regime, trying to communicate with some website, some server, located outside that censoring regime. And of course, this means that there is a nation-state censor between them. Now, commonly, this nation-state censor will employ some form of deep packet inspection, or DPI, to monitor this client's communication. Now, with innocuous communication that the censor is okay with, this communication just passes through. It's monitored, it's observed, but the censor chooses to let it pass. For queries, though, that the censor forbids, for things that the nation state does not want their citizens to be able to access or look up or research, for queries that are forbidden, seeing this query immediately triggers censorship. And at this point forward, the censor immediately moves to actively tear down or otherwise disrupt this communication between the user and the server. Now, there are two broad features of nation-state censorship that govern how these censors react once censorship has been triggered. Now, the first thing we see is that many countries employ what's called residual censorship. And with censors that employ this for a small amount of time after the censor's been triggered, that censorship event you just witnessed, it will continue disrupting all communication between the two hosts, even if that content is benign. So for China, this window of time is about a minute and a half. In Iran, it's a little bit longer. But regardless, if the web browser sends a query to that server, and even if that query is benign or within this window of residual censorship, it will still be affected. And then after that window of time elapses, the censor returns to its normal state of monitoring, but otherwise allowing innocuous network traffic through. Now, a second form of response that we see is censors injecting new content, such as block pages or other packets into the connection. So not just trying to shut down the connection, but actually injecting new content into it. And what this looks like is we have our web browser once again going to issue a query that the nation state forbids. And instead of moving to shut down that connection, the censor actually instead impersonates the destination website that the user was trying to visit and uses that impersonation to send back an error page, a block page, or some other traffic to the web browser in such a way that it looks like it's coming from the server. Now, these two features of censorship infrastructure have been studied extensively, with particular focus on what kinds of harm these can have on people living within the censoring regime. But our work recently has shown that attackers can weaponize this infrastructure and turn it outwards, and use and abuse this censorship as a weapon against both citizens within these countries and the rest of the world. So to explain how this happens, I'm going to turn it over to Dave. Dave, please take it away.
Thanks, Kevin. Now, the critical ingredient behind both of these attacks that we're going to talk about is the ability to impersonate someone else when you're sending packets, to send it as with their IP address as the source. Now, it might seem as though there's no way that you could possibly do this on the internet, but in fact, you can very easily do this on the internet from many networks out there. There are some networks that protect against this, but there's still many out there that allow this to happen. So given that capability, here's what an attacker could do to weaponize these two different forms of censorship, starting with residual censorship. The goal here is there's an attacker who wants to keep this client and this server, this blue and purple guys here, from being able to communicate with one another. So what he does is he impersonates this blue host, sends a request across this censor's border for something that would trigger censorship, sending it to this purple host. This triggers censorship, kicks him off into this period of time of residual censorship, so that then all of this is happening unbeknownst to this blue host. Subsequently, when this blue host tries to send a perfectly innocuous query to purple, it ends up getting blocked, even though this blue host had never sent anything causing him to get censored in the first place. Now, it turns out we've performed various experiments for this, and it turns out that for a really modest amount of traffic, an attacker can disconnect two hosts indefinitely. So for instance, in China and Iran, it would just cost about 1.1 megabits per second, which is well below what most of us have at home today. So the big takeaway here is that attackers can exploit a censor's residual censorship to restrict benign communication from crossing the censor's borders. Now, the second form of attack, being able to weaponize block pages or other forms of content that's injected, the idea here is that the censor is going to be outside the censoring regime. And the goal here isn't to block blue or purple from communicating with one another. The goal is to launch a denial of service attack. This is a form of attack which you've probably heard about, where folks try to take down other people's websites or take down services online by just sending huge amounts of traffic to their networks, way more than they can handle, thereby blocking legitimate traffic from getting through. So in this case, the target is this purple host that's outside the censoring regime, same as the red host. And it turns out that this blue host here is just going to be sort of an innocent bystander. Okay. So the idea is the attacker, again, impersonates the target, sends something that would have gotten censored, and in a way that triggers censorship. Now, it turns out sending packets in this way, where you're impersonating somebody else but triggering censorship, in this particular case, it turns out this is something that was long thought not to really be possible, but using a tool that we had developed called Geneva, which is short for genetic evasion. It's a genetic algorithm, a form of artificial intelligence that we developed for evading censorship. We repurposed it for this to learn these new attacks. So it discovered multiple ways to launch these attacks in ways that, going at it by hand, we just, other researchers had never been able to find it. And it turns out what Geneva found is that you can trigger this really easily by just sending a specially crafted sequence of packets. But in any event, you can trigger the censorship from outside in a way that would cause the censor to then insert a block page. So it impersonates itself, it impersonates the intended recipient, this blue host, and sends this block page. Now, what's the big deal here? The goal was not to disconnect them or to get this person blocked. The goal was to try to inject as much traffic as we can. Why does this achieve that? The thing to note is that the request that the attacker had to send is very small, on the order of hundreds of bytes. But what some censors send can be huge, on the order of thousands, millions of bytes. So normally the way we think of this is in terms of the amplification factor. How much is it amplifying the attacker's traffic? So basically just taking the size of the response from the censor divided by the size of the request sent. Prior efforts in denial of service attacks have shown that even just amplification of on the order of hundreds or thousands can be enough to cause massive damage on the internet. So the amplification factors we found, it turns out, are much, much larger than that. So we found about 400,000 different destinations you can send to around the world that will give over 100x amplification, 10,000 that give over 10,000x, 50 different destinations that give over 1,000,000x amplification, and almost 20 different folks that if you just send 2 or 3 packets to them, again, specially crafted, it can cause censors to send traffic to the to the target indefinitely. And in essence, giving us technically infinite amplification. The main takeaway here is that attackers can use censorship infrastructure to launch denial of service attacks at an unprecedented scale. So both of these different attacks, what they show is that attackers can weaponize censorship infrastructure. If there's no other takeaway you get from this talk, it's that what we thought used to be a predominant threat for those living within the borders, it turns out it can be harnessed as a weapon for the entire world. They're a threat to the entire internet. So what can we do about this? Unfortunately, it doesn't really look like there's a simple technical solution to this. As I mentioned, one of the key ingredients here is impersonating somebody else. We could try to get rid of that, but we've been trying to get rid of that on the internet for a very long time. It seems like that's not going to be viable anytime soon. Really, the ideal solution would be to stop censorship, or at the very least make it far less aggressive than it is, to not residually censor people for long periods of time afterwards, to not inject aggressive amounts of data to try to tear people down and try to inject other sorts of information. But again, there's no really clear technical solution. So one of the reasons that we are really excited to engage with the RightsCon community here is to hopefully engage at a different level of solution. We think this is a technical problem that's really in need of a policy-based solution. We'd be happy to engage with any folks to talk about this. For more information about this work, about these attacks, about the potential censors that give rise to these attacks, and to learn more about our work on evading censorship writ large and our tool Geneva, please visit us at censorship.ai. Thanks so much.